The universe, an endless tapestry of stars and galaxies, stretches across the unimaginable vastness of space, with each celestial body spinning in its own dance. Yet, through meticulous observation and the cutting-edge technology at their disposal, scientists have uncovered a profound truth. The universe is not static. It is expanding, continuously and inexorably, in all directions. And this discovery raises a question that has both fascinated and perplexed us for centuries. What is it expanding from? What lies at the very center of it all? Astronomers have mapped the observable universe, which spans an awe-inspiring 93 billion light-years in diameter. This number, though staggering, only represents the portion of the universe that we can see, the region from which light has had enough time to reach us since the Big Bang, some 13.8 billion years ago. Beyond this boundary lies the unknown, a realm that could stretch endlessly, far beyond the reach of our current technology and understanding. At the heart of modern cosmology is the Big Bang theory, which posits that the universe began as a singular, infinitely dense point, a singularity, some 13.8 billion years ago. Since then, it has been expanding outward in every direction. This theory is supported by two pivotal pieces of evidence. The redshift of distant galaxies, a phenomenon indicating that galaxies are moving away from us, and the cosmic microwave background radiation, once a faint glow that serves as a remnant of the universe's earliest moments. These observations confirm that the universe is a dynamic, ever-evolving entity, not a static, unchanging one. As we peer deeper into the cosmos, we encounter phenomena that defy the very fabric of our understanding, like black holes. These are not just mysterious objects, they are fundamental to the way we understand the universe. Black holes are regions of space where gravity is so intense that not even light can escape. They are some of the most captivating and enigmatic features of the universe, pulling us to explore their nature and implications for the very laws of physics. But perhaps the most profound challenge we face is the sheer scale of the universe itself, a concept so vast it stretches the limits of human imagination. The observable universe, measuring 93 billion light-years across, seems incomprehensible. To put that into perspective, a light-year, the distance light travels in 1 year, is approximately 9.46 trillion kilometers. The universe we can observe spans an almost impossible breadth of space, and this is only the portion that has been able to send light our way. Yet, the true enormity of the universe isn't just in its physical size, it lies in its content. More than 2 trillion galaxies, each home to hundreds of billions of stars, along with countless planets, asteroids, and comets. This staggering variety of celestial bodies, each with its own unique characteristics, offers endless possibilities for life, yet it also underscores the complexity and mystery of the cosmos. In this cosmic ocean, Earth is but a tiny speck. Our galaxy, the Milky Way, which seems infinite when viewed from our vantage point, is just one among countless others. Our Sun, which is central to our existence, is merely one of over 200 billion stars within the Milky Way. And our galaxy itself is only a small part of the vast network of stars, planets, and cosmic structures weaving through space. This immense scale serves as both a source of awe and a humbling reminder of our place in the universe. It challenges us to expand the boundaries of our knowledge and technology, to venture beyond the confines of our own planet and into the stars. The pursuit to map, understand, and unlock the secrets of this vast expanse is what drives scientific inquiry, leading to groundbreaking innovations and a deeper understanding of the fundamental laws that govern the universe. As we extend our gaze deeper into the universe, we are also embarking on a journey back in time. The light that reaches us from distant stars and galaxies has traveled across the vast emptiness of space for billions of years, offering us a precious glimpse into the past. This unique characteristic of cosmic observation allows scientists to unravel the mysteries of the universe's history. From the fiery aftermath of the Big Bang to the birth of stars and the formation of galaxies, we are piecing together the intricate story of creation. The sheer scale of the universe, billions of galaxies and trillions of stars, underscores not only the vastness of space, but also the unimaginable potential for diversity and complexity that lies within it. As we venture further into the cosmos, we find ourselves delving into the very makeup of the universe itself. a topic that has captivated the minds of both scientists and curious onlookers for centuries. At its core, the universe is a delicate blend of vast emptiness, punctuated by celestial objects and mysterious forces. To comprehend these components is to begin understanding the intricate tapestry of existence that stretches across space. The backbone of this cosmic expanse is formed by galaxies, massive structures that house stars, planets, nebulae, and various other forms of matter and energy. Stars, particularly, form the most visible component of these galaxies. These nuclear furnaces fuse hydrogen into helium, producing light and heat. Our sun is a prime example, providing the essential energy that sustains life on Earth. Surrounding stars, we find planets, moons, asteroids, and comets, each performing its role in the grand cosmic ballet. Yet what we can observe is only a fraction of the universe's true composition. Dark matter, an invisible form of matter that makes up around 27% of the universe, remains a mystery. It does not emit, absorb, or reflect light, making it undetectable by traditional means. Instead, its existence is inferred from the gravitational effects it has on visible matter, shaping the way galaxies spin and holding galaxy clusters together, despite the fact that visible matter alone cannot account for their gravitational pull. Even more elusive than dark matter is dark energy, which constitutes about 68% of the universe. This mysterious force is responsible for the accelerated expansion of the cosmos, a discovery that has fundamentally altered our understanding of space. Unlike dark matter, which pulls objects together, dark energy seems to push them apart, working in opposition to gravity on the grandest of scales. The remaining 5% of the universe is composed of ordinary or baryonic matter, the very substance of atoms. From planets and stars to humans and the air we breathe, this matter forms the foundation for all known life and the structures that populate our night sky. Beyond the familiar, interstellar and intergalactic spaces are filled with a thin soup of gas and dust, the remnants of dead stars and the building blocks for new ones. In these vast, empty regions, new stars are born within nebulae where clouds of gas and dust collapse under their own gravity, igniting the fusion processes that fuel these stellar giants. Filling the entire universe is the cosmic microwave background radiation, an echo from the Big Bang, the universe's infancy. This faint radiation serves as a relic of the early cosmos, offering us an invaluable glimpse into the universe's first moments and its rapid expansion. Gravitational forces, the unseen architects of the universe, hold it all together. From the orbits of planets to the formation of galaxy clusters, gravity dictates the motion of celestial bodies, shaping the web of galaxies and the vast voids that separate them. Without gravity, the universe would have no structure. It is the force that connects everything, maintaining the delicate balance that allows the cosmos to exist as we know it. Now, let's embark on an exploration of the observable universe, the segment of the cosmos that we can, in principle, perceive from Earth. This concept plays a pivotal role in cosmology, as it defines the boundaries of space from which light or other signals have traveled long enough to reach us since the universe's birth, roughly 13.8 billion years ago. At its core, the observable universe is a vast sphere, with Earth at its center, stretching out to the farthest reaches of space where light has had the time to journey. This journey is constrained by the speed of light, approximately 299,792,458 meters per second, a limit that frames everything we can observe. However, this boundary is not a fixed, static limit. The universe itself has been expanding since the Big Bang, stretching not just matter, but the very fabric of space-time. As the universe expands, so too do the paths that light travels across space, extending the visible universe in ways that constantly redefine our understanding of the cosmos. Within this observable realm, everything is potentially visible and knowable. From the ancient light of the cosmic microwave background radiation, the afterglow of the Big Bang, to the countless galaxies, each teeming with billions of stars and planets, all moving in a grand cosmic dance. These galaxies are not scattered randomly. Rather, they form an intricate, structured cosmic web of filaments and voids, creating a large-scale architecture of the universe that's both beautiful and baffling. The observable universe holds within it all the phenomena and objects that shape our understanding of cosmology. It is here that we study the life cycles of stars, the distribution of galaxies, and even the fundamental laws of physics as they manifest across the cosmos. Yet, it's important to recognize that the observable universe is just a small fraction of the total universe. Beyond its boundary lies the unobservable realm, regions of space so distant that their light hasn't yet had the time to reach Earth. The full extent of the universe remains a mystery, with its true size unknown. Some theories suggest that it may be infinitely large, while others propose it could loop back on itself in ways that challenge our understanding of space and time. By studying the observable universe, scientists can glean critical insights into the overall structure, age, and the fundamental processes that govern the universe's evolution. This investigation is made possible by advanced telescopes capable of capturing light across a vast spectrum of wavelengths, from radio waves to gamma rays, allowing us to peer back in time to the very early stages of the universe. In this quest for knowledge, measuring distances across the universe is one of the most complex and awe-inspiring challenges. To tackle this, astronomers have devised innovative methods like the cosmic distance ladder, a series of techniques that help us gauge how far away celestial objects lie. Each step of this cosmic ladder uses different tools and observations to span the immense distances between us and the most distant galaxies. For objects within our solar system, distances are measured with remarkable precision using radar. By sending radio waves to planets or moons and timing how long it takes for the waves to bounce back, scientists can calculate distances directly. However, this method has its limits, especially when it comes to objects beyond our solar system. To reach further into the cosmos, astronomers turn to the parallax method. For stars relatively close to us, within a few hundred light years, astronomers observe the slight shift in a star's apparent position as seen from two different points in Earth's orbit around the Sun. This tiny yet measurable movement allows scientists to use geometry to calculate the star's distance. The farther the star, the smaller the parallax shift. For more distant objects, such as galaxies, astronomers rely on standard candles, celestial objects with a known consistent brightness. One of the most famous examples of these standard candles is the Type 1a supernova. These exploding stars have a predictable peak brightness, allowing astronomers to determine their distance based on how bright they appear from Earth. By employing these methods, astronomers continue to unravel the mysteries of the universe, inching ever closer to understanding the vast, interconnected cosmos in which we live. And so, by measuring the dimness of distant objects as they appear from Earth, astronomers are able to estimate their distance. The principle is simple. The dimmer the light, the farther away the object. This forms one of the key rungs on what is known as the cosmic distance ladder. Another crucial method involves redshift, a phenomenon where light emitted by an object is stretched to longer wavelengths as the object moves away from us. This shift happens due to the expansion of the universe itself. The greater the redshift, the faster the object is receding, which gives scientists a means to estimate its distance. Redshift is especially valuable when measuring the distance to galaxies far beyond our reach, allowing us to explore the large-scale structure of the universe. What makes these methods even more powerful is that they overlap in certain distance ranges, allowing astronomers to cross-check and refine their measurements. This layered approach has been pivotal in creating a detailed map of the universe's immense scale, unveiling not just the vastness of cosmic distances, but also the rate at which the universe is expanding, a rate known as the Hubble constant. But that leads to an intriguing question. Why can't we see beyond the observable universe? The answer isn't just a matter of technological limits. It's a fundamental boundary, defined by the speed of light and the age of the universe. The universe, at approximately 8 billion years old, has only allowed light from the most distant regions enough time to reach us, marking the edges of what we can observe. In other words, we can't see beyond this boundary because the light from those regions hasn't yet had enough time to travel across the vast distances since the Big Bang. The speed of light in a vacuum is a constant, roughly 299,792,458 meters per second. This universal speed limit sets the maximum distance over which interactions can occur or information can be exchanged. In the context of the universe, it also limits how far we can see. The observable universe stretches out to about 93 billion light years, not because that's the ultimate size of the universe, but because that's the furthest distance from which light has had enough time to reach us. However, there's another factor at play: the expansion of the universe itself. The universe is expanding at an accelerating rate, which means that distant galaxies are moving away from us faster than the speed of light due to the stretching of space. This doesn't violate the universal speed limit because it's not the galaxies moving through space at these speeds, but the space between us and them that's stretching. Light from galaxies beyond the observable universe may never reach us, as the space it must traverse is expanding too rapidly. Moreover, the expansion of the universe also affects the light traveling through it. As the space stretches, so does the wavelength of light, pushing it toward the red end of the spectrum, a phenomenon known as redshift. For galaxies far enough away, this redshift can be so extreme that their light is shifted beyond the visible spectrum and even beyond the range of our instruments, rendering them completely invisible to us. The concept of the observable universe raises fascinating questions about what lies beyond our cosmic horizon. There may be vast regions of space, teeming with galaxies, stars, and phenomena that we will never see. The size of the universe compared to what we can observe remains one of the great mysteries of cosmology. Some theories suggest that the universe could be infinitely large, or at the very least, far bigger than what our instruments can detect. As our technology advances and our understanding deepens, there's hope that we may discover new ways to peer further into the depths of the cosmos, unearthing secrets that have long eluded us. However, the fundamental constraints imposed by the speed of light and the finite age of the universe create a boundary, a cosmic horizon beyond which the universe remains cloaked in mystery. In this vast and incomprehensible expanse, we are left to peer into the depths of space and time, seeking to understand the forces that shape the universe itself. Galaxy formation. Gravity, in its most profound role, is the unseen architect behind the formation of galaxies. Even in the early, nearly uniform universe, tiny fluctuations in density gave rise to regions that were ever so slightly denser than their surroundings. These small imperfections in the fabric of the cosmos began a chain reaction, as gravity gradually pulled more and more matter into these dense pockets, making them even more compact. Over time, these regions became the primordial seeds from which galaxies would be born. As these initial clouds of gas and dust accumulated, gravity took hold, pulling the matter inward. The process of collapse caused these clouds to heat up, eventually igniting the formation of stars. The stars that emerged from this cosmic cauldron were colossal, burning hot, and short-lived, their lives marked by fierce energy and brief existence. When they reached the end of their lives, they exploded in dazzling supernovae, scattering elements like carbon, oxygen, and heavier metals throughout space, elements that would later become the building blocks for the next generations of stars and planets. This process, one of creation and destruction, unfolded over billions of years, with stars, gas, and dust continuously merging and growing, giving rise to the incredible variety of galaxies we observe today. But this process was not driven solely by the matter we can see. Dark matter, that invisible and mysterious substance, played a crucial role. Enveloping galaxies like an unseen scaffolding, dark matter provided the gravitational structure needed to hold galaxies together as they formed and evolved. Though we cannot detect dark matter directly, we know of its existence through its gravitational influence on visible matter and the large-scale structure of the universe. Dark matter is thought to account for roughly 27% of the universe's total mass and energy, compared to a mere 5% for the ordinary matter that makes up stars, planets, and everything else we can see. Its influence in the formation of galaxies is both profound and invisible, but it is central to the cosmic dance of creation. Galaxies themselves come in a stunning array of shapes and sizes. Spiral galaxies, like our own Milky Way, stretch out in graceful arms that swirl around a dense central bulge. Elliptical galaxies, vast and nearly spherical, are collections of stars in more rounded configurations. Then there are the irregular galaxies, whose disordered structure defies any clear shape or pattern. These different forms are not static. galaxies interact and merge with one another, their encounters leading to dramatic transformations in their structure and star-forming activity. These cosmic collisions are key to the dynamic evolution of galaxies. The formation of galaxies, then, is not simply a matter of gravity pulling matter together. It's a complex interplay of forces. Gas dynamics, stellar evolution, and the mysterious, almost ethereal presence of dark matter. As these forces converge, matter forms, stars ignite and perish, galaxies merge and evolve, telling a story of continuous change. This cosmic ballet unfolds across vast stretches of time and space, shaping the universe in ways both beautiful and incomprehensible. When we look up at the night sky, each galaxy tells the tale of this ongoing cosmic evolution from the universe's earliest moments to the intricate, finely structured cosmos we witness today. Dark matter, though invisible to our senses, plays an irreplaceable role in this story. It is the cosmic glue that binds galaxies together, providing the foundation upon which these immense structures can take form. Although dark matter cannot be seen, touched, or detected directly, its influence is undeniable. It exerts its presence through gravity, affecting not only the motion of stars and galaxies, but also shaping the large-scale structure of the entire universe. Understanding dark matter is one of the most important tasks for cosmologists, as it accounts for approximately 27% of the universe's mass and energy content, dwarfing the 5% represented by ordinary matter. The role of dark matter in galaxy formation stretches back to the very beginnings of the universe. In the aftermath of the Big Bang, the universe was a hot, dense plasma of particles and radiation. Despite the apparent uniformity, minute fluctuations in density marked the seeds for the creation of cosmic structures. Dark matter, unaffected by the same forces that govern ordinary matter, began to clump together in these denser regions. As it accumulated, these pockets of dark matter created gravitational wells, areas where the pull of gravity was much stronger due to the concentration of mass. In these regions, the gravitational pull was so powerful that it began to attract ordinary matter, pulling gas into the densest regions. As gas accumulated, it cooled and condensed, creating the first stars and galaxies. Dark matter, in its invisible form, provided the structural backbone for this entire process, enabling the formation of the galaxies we observe today. This interaction between dark matter and ordinary matter is the cornerstone of the cosmic framework in which galaxies and stars are born, evolve, and ultimately merge into the magnificent structures we see scattered across the universe. Furthermore, the distribution and mass of dark matter dictate the very shape and dynamics of spiral galaxies. Galaxies like our Milky Way are believed to reside within vast halos of dark matter that extend far beyond the visible edges of the galaxy. When we examine the rotational curves of these galaxies, which reveal the velocities of stars and gas as they move farther from the center, something extraordinary happens. The expected drop in velocity with distance doesn't occur. Instead, the velocities remain surprisingly flat or even rise slightly. This anomaly points to the presence of a hidden mass, dark matter, that we can't directly observe, but whose gravitational influence is undeniable. On even larger scales, dark matter's effects stretch across the vastness of galaxy clusters. The gravitational pull of dark matter is what binds these galaxies together, preventing them from being torn apart by their own high velocities. In fact, the distribution of dark matter within these clusters can be mapped through a fascinating phenomenon known as gravitational lensing, where the light from more distant objects bends around the mass of the cluster, distorting the appearance of the background objects. This bending serves as a powerful tool for astronomers, allowing us to trace the unseen presence of dark matter in the universe. Dark matter also plays a pivotal role in shaping the large-scale structure of the universe, the cosmic web. This intricate web consists of filaments of galaxies separated by vast voids, and its very formation owes itself to the gravitational influence of dark matter. The presence of dark matter has been the guiding force, shaping the universe's architecture and steering the formation of cosmic structures on a grand scale. In stark contrast to dark matter, dark energy presents an entirely different mystery. It's a force that permeates all of space, exerting a repulsive effect that accelerates the universe's expansion. While dark matter attracts and clumps together, dark energy pushes galaxies apart, accelerating their separation at an ever-increasing rate. Remarkably, dark energy is believed to account for about 68% of the total energy content in the universe, making it the dominant component in the cosmic energy budget. The concept of dark energy emerged in the late 1990s after astronomers observed distant supernovae that seemed to defy expectations. It had long been assumed that the universe's expansion, initiated by the Big Bang, would gradually slow down due to the gravitational pull of matter. Yet, these supernova observations revealed something surprising. The expansion was not slowing down, but instead accelerating. This led to the conclusion that some form of energy, now known as dark energy, was driving this acceleration, a force working against gravity itself. The nature of dark energy remains one of the most profound mysteries in physics and cosmology. Unlike dark matter, which clumps together under gravity, dark energy appears to have a uniform distribution throughout space. One leading theory posits that dark energy is a property of space itself, as suggested by Albert Einstein's cosmological constant. Einstein originally introduced this term into his general theory of relativity to allow for a static universe, later calling it his biggest blunder after the discovery of the universe's expansion. If dark energy truly is a property of space, it suggests that empty space has an inherent energy that pushes outward, influencing the very fabric of the universe. The effects of dark energy are most apparent on the largest scales of the cosmos. As it drives the universe's expansion, dark energy influences the rate at which galaxies move away from each other. This can be observed by measuring the redshift of light from distant galaxies. As dark energy accelerates the expansion, it stretches the wavelength of light traveling through space, causing it to appear redder than it would in a universe without dark energy. Dark energy also carries profound implications for the ultimate fate of the universe. If its density remains constant or increases over time, it could lead to a catastrophic scenario known as the Big Rip. In this scenario, the accelerated expansion of the universe eventually tears apart galaxies, stars, planets, and even atomic particles themselves, unraveling the very fabric of space-time. Black holes are some of the most enigmatic and awe-inspiring phenomena in the universe. They are regions of space where the gravitational pull is so intense that nothing, not even light, can escape once it crosses the event horizon. The immense gravity of black holes distorts space and time, creating a cosmic boundary from which no information can return. So-called the event horizon, this boundary marks the point of no return, a threshold that cloaks the black hole's interior from the outside universe. Here, reality bends and warps beyond comprehension, trapping all that crosses it. The concept of a black hole originates from Einstein's theory of general relativity, a groundbreaking revelation that transformed our understanding of gravity. According to this theory, massive objects create ripples in the very fabric of space-time. The more massive the object, the greater the distortion. And in the case of a black hole, this distortion is so intense, it creates a gravitational well so deep that nothing, no matter, no light, can escape. Black holes form in several ways, but the most common process begins with the collapse of a massive star. When a star, at least 5 times the mass of our sun, exhausts its nuclear fuel, it can no longer counterbalance its own gravity and implodes. For the most massive stars, this collapse results in a supernova, an explosion so violent it can outshine entire galaxies. What remains of this catastrophic event can be so dense that it forms a black hole. But not all black holes are created equal. They come in different types. Stellar mass black holes, formed from the collapse of massive stars. Supermassive black holes, which are millions to billions of times the mass of our sun and sit at the heart of most galaxies, including our very own Milky Way. Intermediate mass black holes, whose formation is still a mystery but which bridge the gap between stellar mass and supermassive types. The study of black holes extends far beyond the realm of academic curiosity. It has profound implications for our understanding of the universe itself. One of the most groundbreaking discoveries in recent years has been the detection of gravitational waves, ripples in space-time created by the collision of black holes. This new method of cosmic observation has opened a window into the universe that previously remained hidden from us, revealing phenomena that were once invisible. Despite their infamous reputation as cosmic vacuum cleaners, black holes don't actively suck in material. Instead, objects spiral inward, much like planets orbiting the sun, due to the curvature of space-time itself. As matter falls into a black hole, it heats up, emitting intense X-rays that can be detected by space telescopes. This is one of the ways astronomers can identify the otherwise elusive black holes. Another intriguing feature of black holes is the phenomenon known as spaghettification. As an object approaches a black hole, the gravitational pull increases dramatically between its nearest and farthest points, stretching it into long, thin shapes, much like a strand of spaghetti. This and other extreme phenomena underscore the mind-bending forces at play near black holes, warping the very fabric of reality. Black holes also raise profound questions about the nature of information and the ultimate fate of the universe. According to quantum mechanics, information cannot be destroyed, yet within a black hole, it seems to vanish. This paradox has puzzled physicists for decades, sparking debates among the greatest minds, including Stephen Hawking, who proposed various solutions to the conundrum, pushing the very limits of our understanding of physics. Turning our focus to neutron stars and pulsars, these celestial bodies represent some of the most extreme objects in the universe. Neutron stars, the remnants left behind after a massive star explodes in a supernova, collapse into an incredibly dense state. The protons and electrons within the star merge, creating neutrons. These stellar remnants pack a sun's worth of mass into a sphere barely 20 kilometers across, creating conditions where quantum mechanics and general relativity intersect in ways we can't replicate on Earth. Pulsars, a particular type of neutron star, emit powerful beams of electromagnetic radiation from their magnetic poles. As the pulsar spins, these beams sweep through space like the beam of a lighthouse, offering a remarkable natural beacon that astronomers can track across vast distances. These objects, like black holes, are windows into a universe that defies our everyday understanding of physics, inviting us to explore the most extreme and fascinating corners of existence. When Earth intersects the path of pulsar beams, we detect pulses of radiation at regular intervals, earning them the name pulsar. These precise pulses allow for detailed measurements, offering invaluable insights into the cosmos. One of the most groundbreaking contributions of pulsars to science came in the 1970s, with the indirect confirmation of gravitational waves. Astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system, a pair of neutron stars orbiting one another, one of which emitted pulses. As they monitored the system, they noted that the orbit of the pulsar was gradually shrinking, a phenomenon that aligned with the predicted energy law of gravitational waves, as outlined in Einstein's theory of general relativity. This discovery not only earned them the Nobel Prize in Physics in 1993, but it also provided compelling evidence for the existence of gravitational waves, which would be directly detected years later. Beyond this, pulsars serve as natural laboratories for exploring the universe's most extreme conditions. The density within a neutron star is so intense that atoms are crushed into a state known as neutron degenerate matter. Within these stars, conditions may even allow for the formation of strange matter, an exotic form of matter more stable than the nuclear matter we know. By studying pulsars, scientists can explore the behavior of matter at nuclear densities and test the limits of our understanding of nuclear physics. Neutron stars, particularly those in binary systems with other neutron stars or black holes, also offer a unique opportunity to test predictions of general relativity in environments of extreme gravity. This includes phenomena like gravitational lensing and time dilation, which occur in the intense fields surrounding these dense objects. The precise and regular pulses of pulsars have proven invaluable as cosmic clocks. These clocks have been used to conduct experiments in relativistic physics, enhancing our understanding of the interstellar medium. As pulsar signals pass through varying gravitational fields, they are affected in ways that allow astronomers to map the distribution of matter across the galaxy. Moreover, pulsar-based navigation systems, similar to GPS but for space travel, have been proposed. Such a system could use the known positions and timing of pulsars to navigate spacecraft across vast interstellar distances, providing an autonomous method for interplanetary and even interstellar travel. Quasars, or quasi-stellar objects, are among the most luminous and powerful phenomena in the universe. These incredibly bright centers of distant galaxies are powered by supermassive black holes. As matter spirals into these black holes, it heats up and emits vast amounts of light and other radiation, making quasars visible across unimaginable cosmic distances. Despite their relatively small size, often no larger than our solar system, quasars can outshine the combined light of all the stars in their host galaxies. But quasars are not only striking in appearance, they also serve as cosmic beacons, shedding light on the early universe and offering clues about the formation of galaxies and black holes in the first billion years after the Big Bang. The light emitted by quasars travels billions of years to reach us, meaning we observe them as they were when the universe was still in its infancy. By studying these ancient lights, astronomers can peer back in time, examining the conditions that prevailed in the universe's early stages. One of the key contributions of quasars to our understanding of the cosmos is their role in probing the era of reionization. This crucial period, occurring about 1 billion years after the Big Bang, marks the formation of the first stars and galaxies. The radiation they emitted began ionizing the hydrogen gas that filled the early universe, making it transparent to ultraviolet light. Quasars, with their intense radiation, are thought to have played a pivotal role in this process. By analyzing the light from distant quasars, particularly how it interacts with the intergalactic medium, astronomers are able to gain vital information about the state of the universe during its formative years. During and after reionization, quasars become a unique and invaluable tool for studying the early universe. As the light from a quasar journeys toward Earth, it passes through intergalactic gas and dust. This gas absorbs light at specific wavelengths, leaving behind distinctive imprints in the quasar's spectrum, known as absorption lines. These lines serve as a cosmic map, revealing the distribution of matter between the quasar and Earth. The technique used to decipher this information, called the Lyman alpha forest method, has uncovered an intricate network of gas clouds and filaments in the early universe. This discovery allows astronomers to explore the large-scale structure of the cosmos, shedding light on the fundamental makeup of the universe during its infancy. Furthermore, the relationship between quasars and the supermassive black holes at their centers offers profound insights into how these cosmic giants grow and shape their host galaxies. The luminosity of quasars, along with the speed of the material swirling around their black holes, provides crucial clues about the mass of the black holes and the dynamics of their accretion disks. By studying these properties, scientists can refine their understanding of galaxy evolution, including the co-evolution of galaxies and their central black holes. The Big Bang theory remains the leading explanation for the origin of the universe. At its core, it proposes that the universe began as an infinitely small, infinitely dense point, referred to as a singularity, that suddenly expanded around 13.8 billion years ago. This expansion is not a blast from a specific location in space. Rather, it represents the expansion of space itself, meaning that every point in the universe is moving away from every other point. This idea is backed by several lines of evidence, one of the most compelling being the discovery of cosmic microwave background, CMB radiation in 1965, a faint glow that originated from the early universe. The CMB provided a snapshot of the universe's infancy, showing it was hot, dense, and nearly uniform, with slight variations that would eventually give rise to the galaxies and cosmic structures we observe today. Another key observation comes from Edwin Hubble's groundbreaking work in 1929, where he discovered that galaxies are receding from us in all directions, with galaxies farther away moving faster. This observation supports the prediction of the Big Bang theory. The universe is expanding. Furthermore, the theory explains the abundance of the lightest elements, hydrogen and helium, found throughout the cosmos, which were formed during the early moments after the Big Bang, in a process known as nucleosynthesis. As the universe continued to expand and cool, matter began to clump together under the force of gravity, eventually forming stars, galaxies, and, over billions of years, the largest structures in the universe. The Big Bang Theory offers a comprehensive framework for understanding phenomena such as cosmic background radiation, the distribution of galaxies, and the chemical composition of the universe. It's important to note that the Big Bang was not an explosion occurring in space, but rather an expansion of space itself. This distinction is crucial in understanding that the universe can expand from a singular point without having a specific center from which it radiates. Every point in the universe is moving away from every other point, illustrating the vast and continuous nature of this cosmic expansion. The Big Bang Theory has evolved significantly over time. Initially, it was met with skepticism, with some scientists advocating for alternative models like the steady-state theory, where new matter is continuously created as the universe expands. In 1949, the term Big Bang was coined by Fred Hoyle during a BBC radio broadcast, meant to mock the idea of a universe emerging from a singular event. Despite this, the theory gained traction as technological advancements, theoretical breakthroughs, and increasing observational evidence began to support it. Today, the Big Bang Theory also incorporates newer observations, such as the accelerating expansion of the universe, which is attributed to dark energy. However, despite its success in explaining many of the universe's mysteries, the theory still leaves numerous questions unanswered. What is the true nature of dark matter and dark energy? What exactly caused the Big Bang, and was there anything before it? These questions continue to challenge our understanding of the cosmos, prompting ongoing exploration and discovery. The concept of the Big Bang has come a long way since its inception. What once seemed like a speculative hypothesis has transformed into the cornerstone of modern cosmological theory, a journey driven by the ever-expanding frontier of human knowledge. However, the steady-state theory would eventually give way to the overwhelming evidence supporting the Big Bang model. One of the pivotal turning points in the evolution of cosmological theory came in 1965 with the groundbreaking discovery of cosmic microwave background, CMB radiation, by Arno Penzias and Robert Wilson. This faint cosmic afterglow, predicted by theorists like George Gamow, Ralph Alpher, and Robert Herman, provided the first tangible evidence of the universe's hot, dense origins. It strongly bolstered the Big Bang model and undermined the steady-state theory. As we advanced in our technological capabilities, satellites like COBE, Cosmic Background Explorer, WEP-MAP, Wilkinson Microwave Anisotropy Probe, and Planck mapped the CMB in increasing detail. These observations confirmed not just the existence of the CMB, but also deepened our understanding of the universe's age, composition, and the distribution of matter across its vast expanse. The data reinforced key predictions of the Big Bang Theory, including the age of the universe and the presence of large-scale structures in the cosmos. Further refining the Big Bang model, the theory eventually incorporated the concept of inflation, proposed by Alan Guth and others in the early 1980s. This rapid expansion of space in the first fractions of a second after the Big Bang explained the observed uniformity of the CMB across vast distances and the formation of the large-scale structures we see today. Inflation provided a compelling solution to key questions about the early universe's symmetry and its growth. Then, in the late 1990s, astronomers discovered that the universe's expansion was not only continuing, but accelerating. This discovery, derived from observations of distant supernovae, introduced the concept of dark energy, a mysterious force that makes up about 68% of the universe and is responsible for pushing galaxies apart at an ever-increasing rate. This was an unexpected twist, as the original Big Bang Theory did not predict such a phenomenon. Today, the Big Bang Theory is no longer just about the universe's initial expansion. It has evolved into a comprehensive framework that explains the formation of the first particles, atoms, stars, galaxies, and the dynamic, evolving cosmos we observe today. The theory merges quantum mechanics, particle physics, and Einstein's theory of general relativity, creating a unified model for understanding the universe. Let's now focus on the CMB. The cosmic microwave background is the faint light that bathes the universe, an ancient remnant from the early cosmos shortly after the Big Bang. This radiation, which is the oldest light we can detect, provides a snapshot of the universe just 380,000 years after its inception. At that time, protons and electrons combined to form neutral hydrogen atoms, allowing light to travel freely for the first time. The CMB is essentially the afterglow of the Big Bang, stretched and cooled to microwave wavelengths by the continuous expansion of the universe over billions of years. The discovery of the CMB in 1965 by Penzias and Wilson was a game changer, providing critical evidence that the universe had indeed begun from a hot, dense state. What makes the CMB invaluable to cosmology is not just its existence, but its uniformity. Temperature variations across the sky are minuscule, only 1 part in 100,000. These tiny fluctuations, however, are incredibly significant because they mark the seeds of all future structure in the universe, the galaxies, stars, and planets we observe today. The CMB's subtle variations also offer crucial insights into the universe's composition, its geometry, and its evolution. By studying these patterns, scientists can infer the balance of matter and energy, the overall shape of the universe, and even the rate at which it is expanding. The temperature of the CMB is astonishingly consistent, sitting at around 2.7 Kelvin, about -270.45 degrees Celsius, just a fraction above absolute zero, where all motion theoretically stops. This uniformity reinforces the principle of isotropy, meaning the universe appears the same in every direction, a fundamental concept in modern cosmology. Over the decades, missions like COBE, WMAP, and Planck have mapped the CMB with remarkable precision, allowing us to fine-tune our understanding of the universe's earliest moments. These observations have been instrumental in determining the universe's age, about 13.8 billion years, and have provided invaluable insights into the dynamics of space-time, the early universe's inflationary period, and much more. The more we study the CMB, the clearer it becomes that it is not just a relic of the past, but a key to unlocking the deeper mysteries of the cosmos. Space-time is not just a concept, it's the very fabric of the universe, intertwining the 3 dimensions of space with the 4th dimension of time into a seamless 4-dimensional continuum. This framework, central to our understanding of the cosmos, was revolutionized by Albert Einstein in the early 20th century under his theory of relativity. It presents a radical departure from previous notions, showing that space-time is far from static. Rather, it can be warped and curved by mass and energy. And it's this curvature that gives rise to gravity, our perception of an invisible force acting upon us. But gravity is not the simple force Isaac Newton described, operating over vast distances. Einstein's general theory of relativity shifted the paradigm, revealing that massive objects like stars and planets don't merely exert a force, they shape and distort the very fabric of space-time itself. This warping of space-time is what we experience as gravity. It's not just an interaction, but a profound alteration of the universe's structure. Picture space-time as a trampoline. Place a heavy ball in the center, and the surface curves under its weight. Now, roll a smaller ball across it. The smaller ball doesn't just move towards the larger one because of a force pulling it directly. It moves along the curved path caused by the depression in the trampoline. This simple analogy helps visualize how massive objects like planets and stars curve space-time, guiding the motion of other objects around them. The more massive the object, the deeper the curve it creates in space-time. For example, the gravity of Earth affects everything on its surface and the satellites orbiting around it. Yet the Sun, much more massive, creates an even more profound curve, keeping the planets, including Earth, locked in orbit. This was once a mystery, unsolved by Newton's laws alone, but perfectly explained by Einstein's theory. And it doesn't stop at space. The curvature of space-time also affects time itself. Near a massive object where space-time is significantly curved, time slows down compared to a region of weaker gravitational pull. This phenomenon, known as gravitational time dilation, has been confirmed by experiments. For instance, atomic clocks on satellites in orbit tick slightly faster than those on Earth's surface. It's a subtle effect, but one that has profound implications. The most dramatic examples of time dilation and the warping of space-time occur near black holes. At the event horizon, the boundary beyond which nothing, not even light, can escape, space-time is curved so intensely that the escape velocity exceeds the speed of light. This extreme curvature leads to mind-bending time dilation, where time itself stretches to a near halt. Moreover, gravity's influence on spacetime doesn't only affect us on a local scale. It also causes ripples in the fabric of spacetime itself, known as gravitational waves. These waves, created when massive objects like black holes or neutron stars collide, carry energy away from these cataclysmic events. Predicted by Einstein, they were first directly detected by the LIGO and Virgo observatories, opening an entirely new window for observing and understanding the universe. Space-time is not a passive stage where events unfold. It's an active, dynamic participant. The presence of mass and energy deforms space-time, and this deformation dictates the motion of objects. This interplay is described by Einstein's field equations, a set of 10 interconnected differential equations that lie at the heart of general relativity. These equations also have profound consequences for how we understand time. Time is not absolute. It changes depending on how fast an observer is moving or how strong the gravitational field they're in. This phenomenon is known as time dilation. For example, clocks aboard satellites orbiting Earth tick slightly faster than those on the planet's surface. This difference is critical for the accuracy of the Global Positioning System, GPS, which accounts for these variations to maintain precision. Thus, space-time is far more than a mere backdrop for the universe's events. It is a living, breathing entity, shaped by mass and energy, and in turn shaping the behavior of everything within it. It tells us how to move, how to think, and how to measure the very passage of time itself. Space-time challenges our very understanding of reality, revealing that our intuitive grasp of simultaneity is deeply flawed. Events that appear simultaneous to one observer may occur in a completely different sequence to another observer moving at a different velocity. This highlights the relative nature of time itself. Then there are wormholes, hypothetical shortcuts through space-time that have captivated both scientists and the general public. These theoretical passages offer the tantalizing possibility of connecting distant points in the universe. Rooted in the equations of Albert Einstein's general theory of relativity, wormholes suggest that the fabric of space-time itself can be manipulated, bending and twisting in ways that drastically reduce travel distances and times. This concept challenges our very understanding of space, distance, and time. In theory, a wormhole could consist of two mouths connected by a throat, bridging vast cosmic distances, or even offering access to different universes or timelines. The very idea of a wormhole weaves together core elements of modern physics, such as the curvature of spacetime and quantum mechanics. These tunnels might exist at the quantum level as tiny, fluctuating passages. Among the various types of wormholes discussed in theoretical physics, the most commonly considered is the Schwarzschild wormhole, also known as the Einstein-Rosen bridge, after Albert Einstein and Nathan Rosen, who proposed it in 1935. However, despite the intrigue surrounding them, these wormholes would likely collapse too rapidly for anything to traverse them, based on our current understanding. For a wormhole to remain stable enough to be traversable, theoretical physics suggests the need for exotic matter with negative energy density to hold it open. This requirement presents a significant challenge, both conceptually and practically, to our understanding of the universe and the materials that make it up. If a stable, traversable wormhole could be created or discovered, it would revolutionize our grasp of space and distance. Travel that currently takes light years could be accomplished in the blink of an eye, allowing humanity to leap across the cosmos. Such a breakthrough would not only transform space travel, but would also challenge our understanding of causality and connectivity within the universe. Wormholes could unlock new possibilities for scientific exploration, enabling us to study distant stars, galaxies, and planets up close within a human lifetime. They could offer practical routes for interstellar travel and communication, breaking down the vast cosmic distances that currently make such endeavors unfeasible within a reasonable time frame. However, the existence of traversable wormholes remains purely speculative. Despite being fascinating solutions to the equations of general relativity, there is no empirical evidence to support their existence yet. The need for exotic matter raises profound questions about whether such phenomena could exist in our universe and whether future technologies could harness their potential. Beyond their scientific implications, wormholes also provoke deep philosophical inquiries. They challenge our concepts of separation, isolation, and even the fundamental nature of the universe. If wormholes could allow for travel across time as well as space, they would open up a whole new realm of questions. Could they alter causality? What does this mean for free will? How does this affect our understanding of the structure of time itself? The notion of a center to the universe is similarly perplexing and directly contradicts our intuitions. The idea of a cosmic center fundamentally challenges our understanding of the universe's structure. The Big Bang theory, the prevailing model of cosmology, suggests that the universe began from a state of extreme density and temperature and has since been expanding. Yet, this expansion does not imply that the universe is expanding into something or that it originates from a central point. Rather, it means that every part of the universe is moving away from every other part, much like dots on a balloon move farther apart as the balloon inflates. This analogy helps us understand that, although the universe is indeed expanding, it does not have a specific center from which that expansion emanates. Furthermore, observations of the cosmic microwave background radiation, the afterglow of the Big Bang, reveal a universe that is isotropic. This means it appears the same in all directions, with an extraordinary degree of precision. Such uniformity supports the notion that there is no special point in the universe, not even a central one, based on its large-scale structure. The concept of a centerless universe is counterintuitive. After all, our everyday experiences with physical objects tell us that everything has a center. However, the universe's structure and expansion obey the laws of general relativity, not classical Newtonian physics, which governs most of our everyday experiences. According to general relativity, it is space-time itself that is expanding, not individual objects moving through space. This expansion happens uniformly across its infinite or sufficiently vast and curved expanse, rendering the idea of a center irrelevant. In models where the universe is finite but unbounded, much like the surface of a sphere, asking for the center of the universe is akin to asking for the center of the Earth's surface. There is no central point on the surface itself. Instead, every point can be viewed as equally central or equally peripheral, depending on one's perspective. The shape of the universe, whether it is flat, open, or closed, remains one of the most fundamental questions in cosmology. This question hinges on the universe's overall geometry and its fate, both of which are intimately tied to the universe's density. The key factor here is the density parameter, omega, which compares the actual density of the universe to the critical density required for it to be flat. According to Einstein's theory of general relativity, if omega equals 1, the universe is perfectly flat, much like a Euclidean space. In this flat universe, parallel lines never meet, and its geometry mirrors our everyday understanding. While the universe's expansion would slow down over time due to gravity, it would never actually stop or reverse. Recent measurements of the cosmic microwave background, CMB, particularly from the WMAP and Planck satellites, suggest that the universe is extremely close to being flat, with omega near 1. This finding points to a universe that is either perfectly flat or so close to flat that the difference is negligible. If omega is less than 1, meaning the actual density of the universe is lower than the critical density, the universe is considered open. In this scenario, it would expand forever at an accelerating rate, with hyperbolic geometry where parallel lines diverge. However, current observations, including studies of the CMB and galaxy distributions, suggest that the universe is not open. On the other hand, if omega exceeds 1, meaning the universe's density is greater than the critical value, the universe is closed. It has positive curvature, similar to the surface of a sphere, where parallel lines eventually meet. In such a closed universe, gravity would eventually halt the expansion, leading to a contraction or, in the worst-case scenario, a big crunch. Yet, current data does not support this closed model either. Instead, observations suggest that the universe's density is very close to the critical value, meaning it is flat or nearly so. The consensus among cosmologists, based on the latest observations, is that the universe is indeed flat or so close to flat that any deviation is indistinguishable. This flatness has profound implications for the universe's future. It suggests that the universe will likely continue to expand indefinitely, though at an accelerating rate propelled by dark energy. The true nature of dark energy and its influence on the universe's long-term evolution remains one of the most pressing and mysterious questions in modern cosmology. The shape of the universe, along with the idea of a center, is deeply tied to our understanding of cosmology and the very fabric of space-time. If, as current evidence suggests, the universe is flat or nearly flat, this has profound implications for our notion of a central point in the cosmos. In a universe that extends infinitely in all directions, the idea of a traditional center simply doesn't apply. The Big Bang wasn't an event that happened at a single point in space, but rather it occurred everywhere, all at once. In this sense, every location in the universe could be considered both the center and not the center simultaneously. This paradox is much like asking for the center of an infinite plane. While you can arbitrarily pick any point as a reference, no one point serves as the source from which everything radiates. The challenge becomes even clearer when we consider the universe's uniform and isotropic expansion, meaning it looks the same in every direction, expanding evenly from any vantage point. This expansion, observed in the movement of galaxies and the cosmic microwave background radiation, indicates that all parts of the universe are receding from each other, without any identifiable central origin. In theoretical models where the universe might have positive curvature, closed, or negative curvature, open, the idea of a center becomes even more elusive. A closed universe, akin to the surface of a sphere, does not have a center within its three-dimensional surface. Instead, the center of curvature would exist in a hypothetical fourth spatial dimension, one that remains inaccessible and invisible to us. Similarly, in an open universe where space extends infinitely in all directions with hyperbolic geometry, there is no central point. Current evidence suggests the universe is flat or nearly flat, which points to the conclusion that it lacks a center in any conventional physical sense. This realization marks a significant shift from the Earth-centric or sun-centric models that once dominated our understanding of the cosmos, guiding us toward a much more nuanced and complex view of the universe's structure. The way galaxies are distributed across the cosmos is far from random. It forms a vast, intricate structure known as the cosmic web. This web-like arrangement consists of dense clusters of galaxies connected by vast filaments galaxies, all separated by enormous voids of empty space. This structure owes its existence to the gravitational influence of dark matter, an invisible substance that accounts for about 27% of the universe's mass. Although dark matter itself cannot be seen, its presence is inferred from the way it exerts gravitational effects on the visible matter around it, such as the galaxies that light up our night sky. Galaxies are drawn together by gravity, forming clusters that can contain hundreds or even thousands of galaxies bound by their mutual gravitational attraction. These clusters can span millions of light years across. In between them, there are thinner stretches of galaxies, the filaments that form the overall structure of the cosmic web, bridging the gaps between clusters and superclusters. Superclusters are even larger formations, comprising many clusters and groups of galaxies that can stretch over hundreds of millions of light years. Our own Milky Way galaxy is part of the local group, which in turn is part of the Virgo supercluster. The voids between these galactic structures are enormous regions of space with very few galaxies. These voids, which can span tens or even hundreds of millions of light years, may seem empty, but they play a crucial role in the cosmic web, influencing the movement and arrangement of galaxies and clusters on the largest scales. The distribution of galaxies within the universe was shaped by tiny density fluctuations in the early universe, fluctuations that were amplified by cosmic inflation shortly after the Big Bang. These variations in density became the seeds for the cosmic web, which grew under the influence of gravity over billions of years. Dark matter clumped together in these denser regions, pulling in normal matter and helping to form stars and galaxies. Observations from powerful telescopes and satellite missions, such as the Sloan Digital Sky Survey and the Hubble Space Telescope, have mapped out this cosmic web in incredible detail, revealing the intricate filamentary structures that connect galaxies across the universe. These observations have confirmed many of the predictions made by cosmological models and simulations, allowing astronomers to better understand the large-scale structure of the universe and its evolution over time. Telescopes, as remarkable tools, have significantly extended our view of the universe. They enable us to observe objects billions of light years away, giving us the rare ability to look back in time and explore the universe in its early stages. They do so by collecting and focusing light, as well as other forms of electromagnetic radiation from celestial objects. This radiation is then analyzed to determine key properties like an object's composition, distance, and motion. Telescopes extend our view of the universe primarily by gathering faint light over large areas and extended periods, magnifying distant objects so that they become visible or detectable from Earth. The larger a telescope, the more light it can collect. This is why there is an ongoing effort to build even bigger telescopes, or telescope arrays. Telescopes operate across the entire electromagnetic spectrum, from radio waves to gamma rays, with different types designed to capture different wavelengths. Optical telescopes, for instance, collect visible light using lenses or mirrors. These telescopes range from small backyard models to large ground-based observatories and space telescopes, like the Hubble Space Telescope. Optical telescopes have captured some of the most breathtaking images of our universe, from the intricate bands of Jupiter to faraway galaxies. Radio telescopes focus on collecting radio waves emitted by celestial objects. These can be ground-based, such as the Very Large Array in New Mexico, or space-based. Radio telescopes have played a key role in discovering cosmic phenomena that optical telescopes cannot detect, such as pulsars, and have been crucial in mapping the cosmic microwave background radiation. Infrared telescopes detect infrared light, which can penetrate dust clouds more effectively than visible light. This allows astronomers to peer into regions of space that optical telescopes cannot access. Notable examples like the Spitzer Space Telescope and the James Webb Space Telescope are designed to capture infrared light, providing groundbreaking insights into star formation and the early universe. X-ray and gamma-ray telescopes detect the high-energy emissions that arise from the most extreme and violent processes in the universe, such as supernovae, black holes, and neutron stars. Instruments like the Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope have broadened our understanding of these fierce environments. By analyzing the light and other radiation collected by telescopes, astronomers can determine more than just the location of celestial objects. They can assess their chemical composition, temperature, mass, and velocity. This wealth of information has led to discoveries such as the accelerating expansion of the universe, the existence of exoplanets, and the intricate structure of the cosmic web. Telescopes have played a pivotal role in confirming theories of relativity, shedding light on the life cycle of stars, and providing a window into the universe's conditions shortly after the Big Bang. They've also been instrumental in identifying dark matter through its gravitational effects and in the search for dark energy. Launched into orbit around Earth on April 24, 1990, the Hubble Space Telescope has revolutionized our understanding of the cosmos over the past decades. Positioned above the Earth's atmosphere, Hubble captures images and data with a clarity that ground-based telescopes cannot match, free from the blurring effects of the atmosphere. This unique vantage point has allowed Hubble to make numerous groundbreaking contributions to astronomy, such as providing insights into the age of the universe, the existence of dark matter, the accelerating expansion of the cosmos, and the characteristics of exoplanets. One of Hubble's significant achievements has been in determining the age of the universe. Hubble helped refine measurements of the Hubble constant, which is the rate at which the universe is expanding. By observing distant galaxies and measuring their redshifts and distances, Hubble helped narrow the age of the universe to approximately 13.8 billion years. This discovery is a vital piece in understanding the universe's evolution from the Big Bang to the present day. While Hubble did not discover dark matter, its observations have provided strong evidence for its existence. By mapping the distribution of galaxies and observing gravitational lensing, where the gravity of a massive object distorts space, bending light from objects behind it, Hubble has visually demonstrated how dark matter influences the structure and motion of galaxies and galaxy clusters. In the late 1990s, observations from Hubble led to a groundbreaking discovery. The expansion of the universe is accelerating rather than slowing down, as was previously believed. This acceleration is attributed to dark energy, a mysterious force that permeates all of space. This discovery was so profound that it was awarded the Nobel Prize in Physics in 2011. Hubble has played an essential role in the exploration of exoplanets, planets that exist beyond our solar system. Through its powerful instruments, it has captured in-depth observations of the atmospheres of numerous exoplanets, identifying key elements such as sodium, hydrogen, and even water vapor. These findings are critical for understanding the composition and conditions of distant worlds, contributing significantly to the search for planets that may support life. Through its remarkable deep field images, Hubble has also looked back in time, offering a glimpse into the early formation of galaxies. These images, which span vast distances and time periods, have allowed astronomers to study the evolutionary journey of galaxies, transforming from chaotic clouds of stars to the more structured, intricate forms that we observe today. Hubble's contribution doesn't stop there. It has captured stunning images of nebulae, the birthplaces of stars, as well as the intricate remnants of stars that have ended their life cycles in explosive supernovae. These observations have provided valuable insights into the life cycle of stars, from their formation in nebulae to their eventual demise, enriching our understanding of the universe's dynamic and ever-changing nature. Hubble has also studied Cepheid variables, a type of star that serves as a standard candle for measuring cosmic distances. By observing these stars, astronomers have been able to refine the cosmic distance ladder, a series of methods used to measure the vast distances between celestial objects. This refinement has played a crucial role in shaping our current understanding of the universe's true scale. As we continue to unravel the mysteries of the cosmos, global collaboration among observatories has become more important than ever. The collective efforts of radio, optical, and space-based telescopes create a vast network of instruments that amplify each other's strengths, offering a comprehensive view of the universe across the electromagnetic spectrum. A vital aspect of this cooperation is the rapid sharing of time-sensitive data. When a telescope detects a transient cosmic event, whether it's a supernova or the collision of neutron stars, the entire global network is alerted. This allows observatories worldwide to direct their instruments towards the event, enabling us to capture the phenomenon across multiple wavelengths, from radio waves to gamma rays, and gather crucial information that would otherwise go unnoticed. One powerful method that has emerged from this international collaboration is interferometry. By linking telescopes separated by vast distances, this technique essentially creates a single, massive telescope with enhanced resolution and sensitivity. A prime example of this is the Event Horizon Telescope project, which produced the first ever image of a black hole's event horizon. By linking radio observatories across the globe, the project created a virtual Earth-sized telescope, allowing scientists to study the black hole at the center of the distant galaxy, M87. Space missions also benefit from global cooperation. Satellites and space telescopes often require expertise, resources, and technology from multiple countries to succeed. The Hubble Space Telescope, the James Webb Space Telescope, and the Chandra X-ray Observatory are just a few examples of how international collaboration has propelled our understanding of the cosmos. These space-based observatories complement ground-based observations, offering a clearer view of the universe free from the distortion caused by Earth's atmosphere. Data sharing is a cornerstone of this collaboration. Many observatories make their data available to the international scientific community, enabling researchers worldwide to analyze and reanalyze the data. This openness accelerates scientific progress, allowing for the discovery of new insights into the workings of the universe, even by those who may not have direct access to major telescopes. Furthermore, observatories collaborate on educational and public outreach initiatives, sharing their discoveries with the global public and inspiring the next generation of scientists and astronomers. Coordinated events, such as live broadcasts of solar eclipses or the appearance of passing comets, help bring the wonders of the cosmos to audiences around the world. In doing so, they foster a sense of wonder and curiosity about the universe that stretches far beyond the scientific community. The Standard Model of particle physics serves as a monumental framework that intricately describes the fundamental particles and forces shaping our universe, except for gravity. Developed over several decades in the latter half of the 20th century, the model seamlessly combines quantum mechanics and special relativity, offering an elegant explanation of how particles interact through three of the four known fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. However, gravity, governed by the laws of general relativity, does not fit within this paradigm, presenting one of the most profound, unresolved mysteries in physics. At its core, the Standard Model is anchored by the building blocks of matter, quarks and leptons. Quarks, of which there are 6 varieties, up, down, charm, strange, top, and bottom, combine to form protons and neutrons, which in turn constitute atomic nuclei. Leptons include electrons that orbit these nuclei, as well as the elusive neutrinos, which interact so infrequently with matter that they often seem invisible. Adding to this family are their more massive counterparts, the muons and tau particles. Each particle has an associated antiparticle possessing opposite electric charges or quantum properties. The model also reveals the messengers of the fundamental forces, gauge bosons. Photons mediate the electromagnetic force, the familiar force behind electricity and magnetism. W and Z bosons are responsible for the weak force, crucial for processes like radioactive decay. Gluons are the carriers of the strong force, holding quarks together within protons and neutrons. And then there's the Higgs boson, a particle predicted by the Standard Model and confirmed by experiments at the Large Hadron Collider in 2012. The Higgs is crucial, providing mass to particles through the Higgs mechanism, a key step in understanding how matter acquires its weight. Yet, despite its groundbreaking success, the Standard Model is far from the ultimate theory of everything. It cannot account for gravity, the force described by general relativity, nor does it explain the dark matter and dark energy that appear to dominate the universe's mass-energy content. It also fails to explain the observed masses of neutrinos, hinting that there may be physics beyond the Standard Model waiting to be uncovered. This opens up an exciting frontier for physicists who are on the hunt for new phenomena, searching for signs of supersymmetry, extra dimensions, or particles that could constitute dark matter. These pursuits could dramatically reshape our understanding of the universe at its deepest levels. The quest to bridge the gap between the Standard Model and a more complete theory of everything has led to the rise of string theory and M theory. These bold, groundbreaking ideas aim to tackle some of the most profound questions in physics by challenging long-held beliefs and proposing a radically different framework for understanding the fabric of the universe. String theory, which emerged in the late 20th century, envisions the fundamental building blocks of reality not as point-like particles, but as one-dimensional strings. These strings vibrate at different frequencies, and each distinct vibration corresponds to a different particle, whether it's a quark, an electron, a photon, or any other fundamental particle. Unlike the Standard Model, which is built on the notion of point particles, string theory suggests that the true essence of the universe is a set of vibrational patterns unfolding in higher dimensions. As the ambition for a unified theory of everything, string theory seeks to unify all fundamental forces, including gravity, within a single cohesive framework. This is a bold challenge to traditional physics, where the Standard Model and general relativity, despite their incredible successes, have remained separate in their descriptions of the universe. Gravity, a force described by general relativity, is incompatible with the quantum nature of the Standard Model. String theory attempts to reconcile this divide, suggesting that at the most fundamental level, all forces and particles arise from the vibrations of a single entity, the string. One of the most radical features of string theory is its requirement for extra dimensions. While we are familiar with 3 dimensions of space and 1 of time, string theory proposes that there are additional spatial dimensions, up to 10 in some versions and 11 in the more advanced M theory. These extra dimensions are thought to be compactified or curled up so tightly that they are effectively invisible to current detection methods. M theory, which builds on string theory, posits an even grander idea that the most fundamental objects in the universe are not one-dimensional strings at all, but multidimensional membranes, also known as branes. In this picture, strings are just one-dimensional examples of a much larger, more complex structure that could redefine our understanding of the universe's architecture. As researchers continue to explore these mind-bending ideas, the promise of string theory and M theory lies in their potential to unify the forces of nature and unlock the deepest secrets of existence itself. M theory aspires to establish a more comprehensive and cohesive framework, integrating not just the particles and forces of the Standard Model, but also gravitational interactions in a quantum context. This ambitious vision holds the potential to pave the way toward a unified theory of quantum gravity. At its core, M theory and string theory challenge our traditional views, proposing a universe vastly more intricate and interconnected than previously imagined. These ideas stretch far beyond the realms of particle physics and cosmology, offering deep implications that extend into mathematics, quantum mechanics, and astrophysics. They hold the promise of unlocking mysteries, such as the true nature of black holes, the evolution of the early universe, and the very fabric of space and time. However, these groundbreaking theories are not without their challenges. The primary obstacle lies in the current absence of direct experimental evidence, making it difficult to test the predictions made by both string theory and M theory. Despite this, the allure of their potential to rewrite the laws of physics continues to drive exploration at the forefront of theoretical science. In parallel, the search for extraterrestrial life draws upon a multidisciplinary approach, blending astronomy, biology, geology, and atmospheric sciences. This expansive inquiry reflects humanity's age-old quest to answer one of our most profound questions: are we alone? Scientists employ a set of criteria aimed at identifying conditions that could support life as we know it, a search that spans light years beyond Earth. At the heart of this search lies water, an essential building block for life. Water serves as a solvent where biochemical reactions occur, making its presence crucial in the hunt for alien life. The search typically focuses on the habitable zones surrounding stars, the region where temperatures are just right for liquid water to exist on a planet's surface. This zone, however, is not a fixed distance but varies depending on the size and temperature of the star. Planets or moons that show evidence of liquid water, either currently or in the past, are considered prime targets for further study. But water alone is not enough. Life requires more than just a liquid medium. It needs an environment in which it can thrive. A stable climate, a protective atmosphere, and the absence of extreme radiation or toxic elements are all critical factors. Scientists analyze the size, density, and composition of exoplanets to assess whether conditions might be suitable for life. The presence of a planet's atmosphere, for instance, can provide key insights into its surface conditions, the potential for greenhouse gases, and whether it harbors a protective magnetic field. Each of these elements shaping the potential for life to endure. In addition to water and a suitable environment, life generates chemical byproducts as part of its metabolic processes. By studying the light spectra emitted from distant planets, scientists can identify gases in their atmospheres that might signal biological activity. Gases like oxygen, methane, and carbon dioxide are of particular interest, as their simultaneous presence, especially when out of chemical equilibrium, could suggest biological origins, much like we see on Earth. Organic molecules, carbon-based compounds that form the building blocks of life, are another critical target in the search for extraterrestrial life. The detection of such molecules, particularly in environments where liquid water is or was present, would be a significant breakthrough. Complex organic chemistry, including amino acids and nucleotides, is considered a precursor to the emergence of life itself. Life on Earth draws its energy primarily from the sun through photosynthesis. However, it can also thrive on chemical energy, as demonstrated by the thriving ecosystems around deep-sea hydrothermal vents. In the hunt for alien life, scientists consider alternative energy sources that might sustain life on planets or moons where sunlight is scarce or non-existent. Ultimately, the search for life beyond Earth is not solely about discovering organisms directly. It's also about identifying environments that could support life or once did in the distant past. This quest takes us from our own solar system, with Mars and the icy moons of Jupiter and Saturn, like Europa and Enceladus, emerging as top contenders, to exoplanets orbiting far-off stars, each offering new hope in our journey to answer the ultimate question of our existence. Recent advancements in telescopic technology and space exploration missions have revolutionized our ability to search for life beyond Earth. Missions like NASA's Mars rovers, the James Webb Space Telescope, and the Transiting Exoplanet Survey Satellite, TESS, have been designed to gather crucial data to address these questions. By studying exoplanet atmospheres, analyzing soil and ice samples from other planets and moons, and detecting faint signals that could indicate life, scientists are broadening our understanding of where and how life might exist across the cosmos. The discovery and study of exoplanets, planets orbiting stars beyond our solar system, has dramatically changed the way we approach the search for extraterrestrial life. Before the 1990s, the idea of exoplanets was purely theoretical. However, the confirmation of planets orbiting other stars has catapulted these distant worlds from the realm of imagination to reality, fundamentally reshaping our understanding of the universe's potential to harbor life. The sheer variety of exoplanets discovered so far has significantly expanded the possibilities for life in the universe. These discoveries span a broad spectrum of planetary types, from gas giants far larger than Jupiter to rocky worlds that could share similarities with Earth. This diversity challenges our preconceived notions of where life might exist, pushing the boundaries of the traditional habitable zone and opening up the potential for life in a wider array of planetary environments. Among the most exciting findings are the exoplanets found in the habitable zone, the region around a star where conditions may be suitable for liquid water to exist on a planet's surface. These so-called Goldilocks planets are of particular interest to scientists, as liquid water is believed to be essential for life as we know it. By studying these planets, along with their size, orbital patterns, and in the characteristics of their host stars, scientists can assess their potential habitability. Technological innovations in telescopic instruments and observation methods have been crucial to the discovery and study of exoplanets. Methods such as the transit technique, which detects planets as they pass in front of their stars, and radial velocity, which measures the gravitational pull of planets on their stars, have provided vital insights. These techniques not only enable the detection of exoplanets, but also offer valuable data about their atmospheres, compositions, and even surface temperatures. The study of exoplanet atmospheres has opened exciting new possibilities in the search for biosignatures, the chemical indicators of life. By analyzing the starlight passing through an exoplanet's atmosphere during a transit, scientists can detect molecules such as water vapor, oxygen, methane, and carbon dioxide. When these molecules appear in specific combinations, they could point to biological processes at work, offering tantalizing hints of life. The future of exoplanet exploration looks even more promising with upcoming missions and next-generation telescopes, like the James Webb Space Telescope. These advancements are set to further enhance our ability to detect and analyze exoplanets, potentially offering direct evidence of life. As technology continues to evolve, the discovery of planets in the habitable zone and the identification of biosignatures may bring us one step closer to answering one of humanity's oldest questions. Are we alone in the universe? The concept of time travel has long captivated both scientists and the general public, sparking debates and theoretical studies within the realms of physics and cosmology. According to current scientific understanding, certain interpretations of the laws of physics suggest that time travel might, in theory, be possible, though the practicalities and implications remain far from fully understood or realized. Albert Einstein's theory of relativity forms the foundation for many time travel hypotheses. Relativity itself is divided into two parts: general relativity, which describes gravity as the curvature of space-time caused by mass and energy, and special relativity, which deals with the physics of objects moving at high speeds and how they experience time. General relativity introduces the concept of time dilation, a phenomenon where time passes at different rates depending on the strength of a gravitational field or the speed at which an object moves through space. Time dilation has been demonstrated experimentally, and it's this concept that fuels much of the ongoing interest in time travel. Under certain conditions, such as near a massive object like a black hole or traveling at speeds close to the speed of light, time can slow down, suggesting that the manipulation of time might one day be within the realm of possibility. Yet the full implications of this idea, especially in terms of traveling backward through time or navigating across different points in the timeline, remain elusive. While time travel might remain a theoretical concept for now, the exploration of these fundamental aspects of physics continues to push the boundaries of our understanding of the universe. And who knows? Perhaps one day, the dream of traveling through time will become more than just science fiction. Clocks on satellites orbiting Earth tick slightly faster than those on the surface. This is due to the weaker gravitational pull in space. Though the difference is minute, it has been confirmed through experiments, and this subtle effect has practical applications. For example, adjustments are made to account for time dilation in the atomic clocks of GPS satellites. While the shift may seem imperceptible, it's a real-world demonstration of the principles laid out by Einstein's theories. General relativity goes even further, predicting the existence of extraordinary phenomena such as black holes. These are regions in space-time where gravity is so intense that not even light can escape. The theory proposes that near a black hole, time would slow down significantly compared to areas further away. This opens the tantalizing possibility of different paths through time. But, despite the theory's intrigue, the extreme conditions near a black hole are such that survival would be impossible, leaving these possibilities more of a theoretical fascination than a practical reality. Another possibility for time travel arises from the concept of wormholes, tunnels in space-time that could theoretically connect distant points across both space and time. If wormholes exist and we could somehow stabilize them, a big if, requiring exotic matter with properties that have yet to be observed, they could potentially serve as conduits for time travel. However, despite the theoretical underpinnings, the existence of wormholes remains speculative, with no empirical evidence to back them up. Quantum mechanics, too, offers scenarios that challenge our classical understanding of time. Certain interpretations of quantum theory suggest the possibility of events occurring before their causes, an idea that upends the conventional flow of time. But while these phenomena might work on microscopic scales, translating them into the macroscopic world of human experience presents immense challenges. Despite these fascinating theoretical possibilities, the practical realization of time travel faces monumental obstacles. One of the biggest hurdles is the potential violation of causality, the fundamental principle that causes precede their effects. Moreover, the enormous energy requirements for such feats place time travel squarely in the realm of science fiction rather than practical science, at least with our current level of understanding and technology. But how do black holes theoretically enable time travel? Theoretical physicists have proposed that the unique structure of space-time around a rotating black hole could provide a potential pathway to travel through time. As an object approaches the ergosphere of a black hole, it could, in theory, take advantage of the black hole's rotation to enter a closed time-like curve, a path through space-time that loops back on itself. This could theoretically allow for travel into the past or the future, depending on the object's trajectory. Another related concept is the wormhole, or Einstein-Rosen bridge, an imagined tunnel that connects two separate points in space-time. If such a tunnel could exist and be stabilized, and if one end of the wormhole were close enough to a massive object like a black hole, the time dilation effect could cause time to pass at different rates at either end of the wormhole. In this scenario, traveling through the wormhole could, in theory, allow for movement not only through space but also through time. However, these theoretical possibilities come with significant caveats. The extreme gravitational forces near a black hole, especially near the singularity, would likely destroy any known form of matter, rendering survival impossible with current technology. Additionally, the existence of stable wormholes, let alone their use for time travel, remains purely speculative. relying on exotic forms of matter with negative energy densities that have yet to be observed. Moreover, these concepts challenge our understanding of causality, the foundational idea that causes precede their effects. Time travel to the past introduces the possibility of paradoxes, like the famous grandfather paradox, where a time traveler could potentially prevent their own existence, creating a loop of impossible scenarios. Quantum mechanics, a realm where the boundaries of reality are stretched to their breaking point, unveils the mysterious behavior of particles at the atomic and subatomic levels. It stands as a stark challenge to classical physics, disrupting long-held beliefs about the universe's predictability. Unlike the predictable, orderly world described by classical physics, quantum mechanics reveals a universe dominated by probabilities and uncertainties, where the rules of cause and effect no longer apply as we once understood them. At the heart of quantum mechanics lies the concept of wave-particle duality. This startling idea demonstrates that particles, such as electrons, are not confined to being either waves or particles. They can simultaneously exhibit both characteristics. It is a direct challenge to the classical notion that entities must belong to one category or the other, suggesting a deeper, more complex reality beneath the surface. Adding to this challenge, the Heisenberg uncertainty principle reveals that there are limits to how much we can know about certain pairs of physical properties, such as position and momentum. The more precisely we measure one, the less accurately we can measure the other. This inherent uncertainty shakes the deterministic foundations of classical physics, where the universe was once thought to be predictable and knowable. Then there's quantum entanglement, perhaps one of the most bewildering discoveries of all. It reveals that particles, no matter how far apart they are, can become entangled, with the state of one instantly affecting the state of the other. Einstein, famously uncomfortable with this idea, referred to it as spooky action at a distance, questioning the very nature of causality and locality in the universe. This profound discovery challenges our fundamental understanding of how information and influence travel across space, leaving us to rethink our assumptions about the fabric of reality itself. Alongside entanglement, the principle of superposition provides another breathtaking insight into the nature of reality. It allows particles to exist in multiple states at once, a paradox famously illustrated by the thought experiment of Schrödinger's cat, in which a cat can be considered both alive and dead simultaneously, until observed. This challenges our daily experience, where objects appear to have a single definitive state. It raises deeper philosophical questions about the role of the observer in shaping the universe, suggesting that reality itself might not exist in a definitive form until it is observed. And then there's quantum tunneling, where particles can pass through barriers that would be impossible to cross according to classical physics. This phenomenon, seemingly defying the basic laws of nature, not only showcases the strange behavior of the quantum world, but also has significant real-world implications. It has played a crucial role in the development of technologies such as transistors and the fusion processes powering stars, altering the course of human progress. In essence, quantum mechanics challenges our classical views of the universe, replacing certainties with probabilities and introducing a world where the act of observation may determine the very state of reality. This paints a picture of a universe far stranger and more interconnected than we had ever imagined, urging us to reconsider not only the nature of particles and forces, but the fundamental structure of reality itself. But let us delve deeper into the enigma of quantum entanglement. Initially, this idea was so perplexing that Einstein could not accept it, dubbing it spooky action at a distance. He saw it as a challenge to the principles of locality and realism, which had dominated physics for centuries. Yet, as experiments continued to confirm the reality of entanglement, our understanding of the universe began to shift in profound ways. Entanglement, far from being an abstract curiosity, now holds the potential to revolutionize fields like quantum communication and computing. While it does not allow information to travel faster than light, thus respecting Einstein's theory of relativity, it does enable instantaneous correlations between distant particles. This has profound implications for creating communication systems that are inherently secure and computing systems that could function at speeds unimaginable by today's standards. Beyond the practical, entanglement also invites us to explore deeper philosophical questions. It forces us to reconsider the nature of connectivity and reality itself, suggesting that the universe might be more intricately woven together than we ever realized. As we peer into this strange and complex world, quantum mechanics not only reshapes our understanding of particles and forces, but challenges the very foundation of how we perceive the universe around us. And so, some theories suggest that entanglement could be a fundamental feature of space-time, possibly tied to the quantum nature of gravity. This idea has ignited speculative yet fascinating possibilities about the universe's interconnectedness. Physicists have begun to wonder whether the Big Bang itself might have entangled particles across the cosmos, creating a hidden web of connections that forms the very foundation of the universe's structure. Though entanglement doesn't allow for the transfer of information in a way that would enable faster-than-light communication or travel, it challenges our deepest assumptions about separation and independence at the most fundamental level. The instantaneous correlation between entangled particles, regardless of the distance between them, suggests a unity in the quantum realm that transcends classical spatial boundaries. It hints at the presence of a deeper, perhaps still undiscovered principle, governing the cosmos in ways that we are only beginning to grasp. Quantum computing, rooted deeply in the principles of quantum mechanics, stands at the threshold of a seismic transformation in computational power and capability. This shift holds the promise of revolutionizing our exploration of the cosmos. Unlike classical computers that rely on bits as the smallest unit of information, quantum computers utilize qubits. These qubits can exist not only in states corresponding to the binary values of 0 or 1, but also in states where they are both 0 and 1 simultaneously, thanks to quantum superposition. Furthermore, qubits can be entangled, meaning the state of one qubit can depend on the state of another, regardless of the distance between them. This unique property vastly enhances the quantum computer's ability to process and analyze information exponentially faster than classical computers. For certain tasks, this leap in computational power could transform our exploration of the universe in profound ways. At the forefront, it would allow for the processing of vast data sets generated by telescopes and space probes with far greater efficiency than currently possible. The cosmos, with its treasure trove of data, from the cosmic microwave background radiation that reveals the early conditions of the universe, to the light from distant stars and galaxies telling us about the expansion of the universe and the distribution of dark matter, could be analyzed swiftly and deeply by quantum computers. This could uncover patterns and correlations that remain hidden to classical computing methods. Quantum computing could also usher in a new era of simulation. Astrophysicists rely on simulations to understand the complex and dynamic processes that govern the cosmos, galaxy formation, black hole behavior, and the distribution of dark matter, to name a few. These simulations are computationally intensive, particularly when trying to model phenomena over cosmic timescales or simulate the interactions of billions of particles. With superior processing capabilities, quantum computers could simulate these processes with a level of detail and speed that classical computers cannot achieve, offering new insights into the fundamental workings of the universe. Another promising application lies in optimizing telescope arrays and planning space missions. Quantum algorithms are uniquely suited to solving optimization problems, which could dramatically enhance the design and arrangement of telescopes to maximize their observational capabilities. Furthermore, these algorithms could optimize the trajectories of space probes, ensuring more efficient exploration of our solar system and beyond. The search for extraterrestrial life could benefit immensely from quantum computing, particularly through the analysis of atmospheric data from exoplanets. Detecting signs of life or biosignatures is a complex task. The precise calculations needed to distinguish these signs from the vast array of cosmic phenomena could be performed much more efficiently with quantum computers. In doing so, quantum computing could accelerate the quest for life beyond Earth, bringing us closer to answering one of humanity's most profound questions. Quantum computing holds the potential to decode the very mysteries of the universe. by significantly enhancing our ability to process information, simulate complex systems, and analyze the signals we receive from the farthest reaches of space. This technology could not only define our exploration of the cosmos, but also deepen our understanding of the fundamental laws that govern it. As this technology advances, it promises to bring us closer to understanding the universe's most profound questions about its nature, its origins, and our place within it. Cosmic voids, those vast expanses of empty space scattered across the universe, are as mysterious as the galaxies and stars that have captivated humanity for centuries. Yet, these voids are not mere absences of matter. They are critical components in the intricate puzzle of the large-scale structure of the universe. Spanning millions of light years, voids are the largest structures in the universe, defined not by what they contain, but by what they lack. They contain few galaxies compared to the universe's denser regions, making them appear as colossal bubbles in the cosmic web, a vast interconnected network of filaments linking galaxies and galaxy clusters, with voids in between. The existence and properties of cosmic voids offer valuable insights into several key areas of cosmology, such as the expansion of the universe, the nature of dark matter and dark energy, and the conditions that prevailed in the early cosmos after the Big Bang. These voids are sensitive to the dynamics of the universe's expansion, offering clues about the evolution of the cosmos itself and helping scientists refine their understanding of the forces and principles that shape our universe. Because their evolution is shaped by the gravitational pull exerted by matter within the surrounding cosmic filaments and sheets, the vast emptiness of the universe stretches ever more as the cosmos itself expands. As voids grow larger, they act like the stretch marks in the fabric of space-time, an imprint of the universe's ongoing transformation. By studying the expansion and evolution of these cosmic voids, astronomers can unlock critical insights into the rate at which the universe is expanding and the mysterious influence of dark energy, the unknown force that is driving this acceleration. Moreover, the intricate shape and distribution of these voids provide vital clues about dark matter, the invisible substance that holds sway over gravitational forces and plays a key role in shaping the large-scale structure of the universe. These voids are formed in areas where dark matter's density is lower than average. By meticulously analyzing the size and distribution of these voids, scientists can test and refine models of cosmic structure formation and explore the enigmatic properties of dark matter itself. The patterns of voids, along with galaxies and galaxy clusters, are echoes of the universe's earliest moments, tiny fluctuations in the density of matter from the cosmos's infancy, captured in the cosmic microwave background radiation that have grown and evolved over billions of years into the vast structures we observe today. The size and spread of cosmic voids serve as a direct link to these primordial conditions, offering valuable insights into the processes that shape the universe in the aftermath of the Big Bang. But voids are more than just a record of the past. They also act as natural laboratories, providing a unique environment for studying the laws of physics under extreme conditions of low density. Here, in these vast empty spaces, the effects of dark energy and the forces of gravity can be studied without the interference of dense matter, offering an ideal setting for testing theories of gravity and examining the behavior of galaxies and intergalactic gas in environments starkly different from our own Milky Way. One of the most captivating and mysterious phenomena in the universe is the Great Attractor, a colossal gravitational anomaly located near the Hydra Centaurus supercluster, roughly 250 million light-years away from the Milky Way. This strange region of space exerts such a powerful gravitational pull that it affects not only our galaxy, but also thousands of others, drawing them towards it at speeds of hundreds of kilometers per second. The discovery of the Great Attractor in the 1970s raised numerous questions for astronomers, especially since it lies in a region of space obscured by the Milky Way's galactic plane, a dense, dust-filled zone known as the Zone of Avoidance, which blocks light from objects beyond our galaxy and makes direct observation nearly impossible. However, despite these challenges, astronomers have used X-ray, infrared, and radio wavelengths to peer through the cosmic dust. These observations have revealed a dense concentration of galaxies and galaxy clusters in the regions surrounding the Great Attractor, suggesting that it is not a singular massive object, but a large and complex concentration of mass. This mass is anchored by a web of galaxy clusters interwoven with dark matter, which contributes to the gravitational force exerted by the Great Attractor. The force is predominantly gravitational, pulling galaxies towards the center of this immense structure, a phenomenon known as gravitational attraction. This motion is part of broader cosmic flows that govern the motion of galaxies across the universe, shaped by the large-scale distribution of matter and energy. The influence of the Great Attractor is so profound that it affects the velocities of galaxies across vast distances, spanning hundreds of millions of light years, revealing the presence of an incredibly massive structure lurking in the dark. Equally fascinating are the rogue planets, celestial bodies wandering alone through the void of space, unanchored by any star system. These mysterious planets, drifting in isolation, present a profound puzzle in our understanding of planetary formation and the broader dynamics of the universe. Their existence challenges our conventional views of how planets form and how star systems evolve over time. Most rogue planets are thought to have been ejected from their original star systems during the chaotic early stages of planetary formation. In these turbulent environments, gravitational interactions with larger bodies or the rearrangement of a system's architecture can send planets and planetesimals hurtling into the vastness of space, where they become solitary wanderers, lost to the gravitational grip of any star. In exploring these cosmic anomalies, whether voids, the Great Attractor, or rogue planets, we are piecing together the grand narrative of the universe's evolution, uncovering the hidden forces and structures that govern the vast and mysterious expanse of space. And then there are the rare yet captivating encounters with passing stars or galaxies, whose gravitational influence can unseat entire planets from their orbits, sending them spiraling into the vast expanse of interstellar space as rogue planets. These planets, freed from the constraints of a host star, range from rocky worlds barely larger than Earth to massive gas giants many times our planet's size. Without the warm embrace of a nearby star, rogue planets remain elusive and difficult to detect. Their discovery often relies on the phenomenon of gravitational microlensing, where their gravity bends and magnifies the light of a distant star as they pass in front of it, a fleeting moment of cosmic alignment. Studying these rogue planets opens a rare window into the universe's hidden past, offering clues about the violent gravitational interactions that shape planetary systems. For example, by analyzing the distribution of mass and the number of rogue planets, scientists can uncover the frequency and intensity of planetary ejection events in young solar systems. These rogue worlds challenge our assumptions about planetary environments and the possibility of life. Some rogue planets, retaining thick atmospheres, may hold onto enough heat from their formation to sustain subsurface oceans, creating intriguing possibilities for life in these dark, wandering realms. The discovery of rogue planets forces us to rethink the boundaries of where planets can exist, revealing that they are not confined to the narrow zones around stars. In a broader sense, these planets help us probe the distribution of matter in our galaxy, including dark matter. As rogue planets drift through space, their gravitational interactions with the cosmos provide indirect evidence of dark matter's presence and properties, which remain otherwise hidden from direct detection. As we peer further into the cosmic abyss, we face the ultimate question: what is the fate of the universe? For centuries, astronomers and cosmologists have grappled with this enigma. With the advances of modern observational techniques and theoretical physics, several leading theories have emerged, each offering a distinct view of the universe's final chapter. These theories are rooted in our understanding of cosmology, particularly the nature of cosmic expansion, dark energy, and dark matter. One of the most widely accepted ideas is that of heat death, or the Big Freeze. This theory posits that the universe will continue to expand indefinitely, stretching out over trillions of years. Stars will burn through their nuclear fuel and extinguish, galaxies will drift apart, and black holes will slowly evaporate through Hawking radiation. the universe will become a cold, dark, lifeless expanse, where temperatures approach absolute zero, as energy becomes evenly distributed across an ever-expanding void. Based on current observations of dark energy, which is accelerating the expansion of the universe, this scenario seems the most probable. Alternatively, there is the Big Crunch, a concept that counters the Big Bang. This theory suggests that the universe's expansion could one day halt and then reverse, causing a catastrophic collapse. Galaxies, stars, and ultimately everything within the cosmos would be drawn back into a singularity, perhaps even triggering a new Big Bang. However, recent discoveries of the universe's accelerating expansion have cast doubt on this scenario, as it appears there may not be enough mass or gravitational pull to halt the expansion. A more dramatic variant is the Big Rip, a theory that hinges on the properties of dark energy. If dark energy grows stronger over time, it could eventually tear apart galaxies, stars, and even atoms themselves. The universe would reach a point where all matter is ripped to pieces at the atomic level, leaving behind a vast, empty expanse where no structure exists. There is also a less discussed but equally fascinating theory, the Big Bounce. This concept suggests that rather than a final end, the universe undergoes an eternal cycle of expansions and contractions. Each cycle ends in a big crunch, followed by another Big Bang, bringing forth a new universe. This cyclical model, while speculative, holds a certain allure, offering symmetry and the tantalizing possibility that our universe is simply the latest iteration in an infinite cosmic rebirth. Lastly, there's the possibility of a quantum death, an event where quantum effects at the smallest scales could cause the decay of the vacuum state of the universe. This decay would trigger the expansion of a bubble of lower energy vacuum racing at the speed of light, altering the very laws of physics within it. In the blink of an eye, the universe as we know it would be unrecognizable. Yet, this scenario remains highly speculative, dependent on the elusive realms of quantum gravity and particle physics, areas we have only just begun to explore. Dark energy, a mysterious force responsible for the accelerating expansion of the universe, stands at the heart of current cosmological models, influencing predictions about the universe's ultimate fate. Discovered in the late 1990s through the observation of distant supernovae, dark energy has been one of the most profound and perplexing forces in modern physics. Despite constituting about 68% of the total energy content of the universe, its true nature remains a mystery, driving research and debate among scientists. At the core of dark energy's role is its influence on the expansion of the cosmos, a power that could shape the universe's future in unimaginable ways. The key question hinges on whether dark energy's strength remains constant over time. If it does, as suggested by Einstein's cosmological constant model, the universe will continue to expand at an accelerating rate. This would send galaxies drifting further apart, stars fading into darkness, and the universe gradually cooling, a chilling scenario known as the Big Freeze or heat death. In such a universe, the distances between matter would stretch so vast that interactions between particles would cease altogether, leaving behind only a cold, empty void. On the other hand, if dark energy's strength grows over time, a far more dramatic and chaotic end could await us. This is the realm of the Big Rip. In this cataclysmic scenario, the force of dark energy would eventually overpower all other forces: gravity, the electromagnetic force, even the bonds that hold atoms together. Galaxies, stars, planets, and ultimately atoms themselves would be torn asunder by the relentless expansion of space, leaving behind a universe where not even the smallest structures could survive. Alternatively, what if dark energy weakened or its effects reversed? This could trigger a slower, more gradual collapse of the universe, leading to the Big Crunch. In this scenario, the universe would contract, collapsing back into a dense, hot state, a possible precursor to another Big Bang and the birth of a new universe. However, given current evidence supporting the accelerating expansion, the likelihood of such a reversal seems increasingly remote. Yet, the most intriguing possibility remains the potential for dark energy to behave in ways we haven't yet imagined. If its properties change in unpredictable ways, the fate of the universe might unfold in a direction we can't yet fathom, challenging every aspect of our current cosmological models. The role of dark energy not only highlights the ever-changing nature of the universe, but also underscores how seemingly intangible forces can dictate the evolution of the cosmos on a grand scale. As we continue to probe the mysteries of dark energy through the study of the cosmic microwave background, distant supernovae, and galaxy clusters, we edge ever closer to understanding not only the ultimate fate of the universe, but also the very fabric of reality itself. The more we uncover, the more we realize just how much we still have to learn about the forces shaping our existence. Human activities stretch far beyond the confines of Earth, casting ripples that reach deep into the cosmos. The vastness of the universe might make it seem like our actions are insignificant in the grand scheme of things. However, certain human endeavors are leaving subtle yet profound footprints in space, marking our presence in ways both direct and indirect. Space exploration, for example, is a prime example of humanity's cosmic interaction. From the Voyager probes, which have now crossed into interstellar space, to the rovers traversing the Martian surface, human-made objects have ventured to the farthest reaches of the solar system. Yet, each mission carries a risk, an ecological footprint that could alter the very landscapes of other worlds. Despite the best efforts to sterilize spacecraft, there's always the chance that Earth's microbes might hitch a ride. If microbial life were to take root on another planet or moon, it could change the course of astrobiology, reshaping our understanding of life beyond Earth. On a more immediate scale, human activities have left a visible imprint on our own planet's surroundings. Orbiting Earth is a growing belt of artificial satellites and debris, a sprawling mass of technological detritus. This space junk poses significant risks to operational satellites and ongoing space missions, but its presence has broader implications. As we continue to launch more satellites, this cloud of debris could become a defining feature of our planet, potentially visible to any advanced civilization observing our solar system. If such civilizations exist and possess the means to study distant worlds, this accumulation of artificial materials may serve as an unmistakable marker of technological life on Earth. Yet the human impact on space is not confined to debris. Our very presence on Earth has consequences that stretch into the cosmos. Light pollution, our artificial night lighting, sends waves of bright energy spilling into the space around us. From above, this glow alters Earth's natural nighttime environment, creating a bright halo around our planet. This shift not only hinders our ability to study the universe through Earth-based telescopes, but it could also be detectable from distant civilizations. To any observer, the change in Earth's nightscape might signal the existence of technologically advanced life, one that is capable of altering its environment on a cosmic scale. The Kardashev scale, a theoretical model that classifies civilizations based on their energy consumption, suggests that as a civilization advances, it could exert increasingly significant influence over its planet or even its galaxy. While humanity has yet to reach a stage where our energy consumption radically alters the solar system, the scale proposes that such developments are inevitable. With time, civilizations could expand their reach and begin to alter the very fabric of the cosmos itself. At the heart of these advancements lies humanity's insatiable curiosity about the universe. Theoretical research, observations, and simulations have already stretched our understanding of the cosmos, unveiling everything from the nature of subatomic particles to the formation of galaxies. These intellectual endeavors leave their own mark on the universe, not through physical artifacts, but through knowledge. By unraveling the mysteries of existence, we contribute to a larger tapestry of understanding that will influence future generations and perhaps even other civilizations that might one day encounter our findings. In exploring our place in this vast expanse, we also encounter the simulation hypothesis, a thought-provoking idea suggesting that our entire reality might be an artificial construct. Popularized by philosophers like Nick Bostrom, this theory posits that an advanced civilization might one day possess the technological capability to create simulations that are indistinguishable from the real world. If such simulations exist, then those living within them, ourselves included, may remain unaware of the artificial nature of their reality, forever trapped in a digital universe that mimics the one we perceive as real. Thus, humanity's reach into the cosmos is multifaceted, both tangible and theoretical, visible and invisible. From satellites and space debris to profound shifts in our understanding of existence itself, our activities are inscribed in the very fabric of the universe. And while the true scope of our impact remains to be fully realized, it's clear that we are part of a larger cosmic story, one that could transcend the boundaries of Earth and echo through the stars. Consider for a moment how we, as individuals, perceive the world around us. Many would argue that our experiences, interactions, and the environment we live in are undeniably real. But what if reality itself isn't what we think it is? The hypothesis that questions our very existence: could we be living in a simulation? This idea isn't just a philosophical musing. It's grounded in several compelling lines of reasoning. Take video game technology as an example. Modern video games have evolved in incredible ways, far surpassing the simplistic, pixelated landscapes of the past. Games now feature vast, immersive worlds with intricate details that feel almost indistinguishable from reality. Proponents of the simulation hypothesis argue that, following this trend, future technology could one day simulate entire universes. These simulations could be so precise, so detailed that the beings within them, artificial though they may be, could possess true consciousness and self-awareness, that experiencing their existence as if it were real. A central pillar supporting the simulation hypothesis is the concept of ancestor simulations. Imagine a future civilization with the capability to simulate the consciousness of their ancestors, recreating entire histories, behaviors, and decision-making processes. If these simulations became commonplace, the argument goes it would be statistically more likely that we, too, are living in one of these simulations rather than experiencing what we consider base reality. However, the simulation hypothesis is not without its critics. Some challenge the feasibility of simulating an entire universe with the level of detail required to create conscious beings. Others raise ethical concerns. If we can create beings capable of suffering, should we? Yet, perhaps the most profound objection comes from the idea that the simulation hypothesis is unfalsifiable. There is no empirical test, no definitive way to prove or disprove that we are living in a simulation. This places the theory outside the scope of traditional scientific inquiry. And then there's the question of consciousness itself. Can consciousness truly be replicated? This question plunges us into one of the deepest mysteries of both science and philosophy. If consciousness relies on a physical substrate, something beyond the reach of digital replication, the simulation hypothesis might crumble under the weight of its own assumptions. As we delve deeper into our understanding of the universe, we've uncovered a surprising truth. The universe expands uniformly in all directions. There is no discernible center. This challenges our ingrained need to find a central point, a prime mover, if you will. Perhaps then, the center of the universe is not a specific location on a map, but rather a concept, a profound idea residing at the heart of our quest for knowledge. In this sense, the center is both everywhere and nowhere, reflecting the depth of human curiosity. Our endless search for understanding places us all at the very center of this cosmic journey, limited only by the boundaries of our perception and the vastness of our imagination. But what do you think? Is there a center to the universe, or has there ever been one? We'd love to hear your thoughts. Leave your comments below, and thank you for watching.